All right, so in this video, I'm going to talk a little bit about time value of money and introduce that concept. Time value of money is likely one of the most important concepts in all of finance. It forms the basis or underpins things like stock valuation, bond valuation, capital budgeting, and many other things really. Think retirement planning, figuring out payments for mortgages. I mean, all those kinds of things. It really comes back to time value of money. So, likely time value of money is probably the most important concept in all of finance, really. And really what it links to is this idea that a dollar today is worth more than a dollar a year from now. So if you were given a choice between a dollar today or a dollar a year from now, you'd pick the dollar today. And there's some reasons why you do that. One, inflation. So if I have a dollar today, I can buy more with that dollar today than I could buy with it a year from now. Investment opportunities. If I have the dollar today, I can invest it and have more than a dollar a year from now due to investing it. And similarly, if I had a dollar today, I could put it in a bank and earn interest on it, right? And so if I had a dollar today, I could have more than a dollar a year from now, which means I value that dollar today more than the dollar a year from now. And really what's sort of underpinning those is really a consumption preference. And that is that if, let's say you really wanted to buy a candy bar, you really wanted, the candy bar just sounded really good to you right now, and somebody wanted to borrow that dollar from you. And if you let them borrow that dollar, you're going to have to wait to buy the candy bar for, let's say, a year. So if that's the case, you are delaying your consumption of the candy bar for a year. And so as a result of that, you don't view the dollar today and the dollar a year from now as equivalent, because if they just return the dollar at the end of the year, well, yes, I got the dollar back, but I had to wait for my candy bar for a year. So, so that's not really equivalent. And so that delay of consumption means I'm going to need to get more than a dollar a year from now for me to feel like this is sort of an even exchange here, because I kind of need compensation for waiting. Whereas if I'd had the dollar now, I could have just bought the candy bar, right? So all that to say, this is an extremely important concept in finance. And the key time value money equation that sort of really kind of guides a lot of the calculations and things that you could do with time value of money is this one. And that is that the future value, or FV, is equal to the present value, or PV, times 1 plus the periodic rate times raised to the number of periods. So let me walk you through this a little bit more. FV is future value. That's some amount at some point in the future. PV, some amount basically now. R is the nominal annual rate. M is the number of compounding periods per year. N is the number of years. So let me give you an example. Let's suppose I had a situation where the nominal annual rate was 10%, so it's just 10% per year. And it's just one compounding period per year. So I'd have 10% divided by 1. So this would just be 10%. And then in the exponent here, I would take the number of years times 1, because it's 1 period per year. And that would be my exponent. If I was doing semi-annual compounding, and then what would happen is I would take my annual rate here, so my 10%, my example, divide it by 2, because there are 2 semi-annual periods within a year. And I would have 10% divided by 2, which is 5% per 6 months. But then up here in the exponent, I would take M, which is 2, times N, the number of years. And that, if I multiply those together, it's going to tell me the total number of periods. And here's why. There's 2 semi-annual periods per year. Then I multiply times the number of years to get to the total number of periods. So significantly, what I wind up with is a rate per period inside the parentheses that is linked to a length of time that matches the number of periods. So in other words, if I have an annual rate here, if that's my periodic rate, it's an annual rate, then I need to have a number of years as my exponent. If I have a semi-annual rate here, if R over M gives me a semi-annual rate, then I need to have the number of semi-annual periods in my exponent. If I'm doing monthly, then I would divide by 12. So my annual rate divided by 12, but then I would take the number of years times 12 to find the total number of months. If I was doing daily, I would take the annual rate divided by 365. Then I would take the number of years times 365 to find the total number of days to use in the exponent. So importantly, when using this formula, the R over M is going to give you a rate per period, and the M times N is the number of periods total. Make sure that those two calculations are linked to the same length of time. So in other words, annual and annual. monthly and monthly, daily and daily. Make sure that things match up. Okay. Now, as m gets larger and larger and goes to infinity, basically what happens is something called continuous compounding. This is more of a side note in most cases. A lot of the times you won't necessarily encounter this unless you are going to certain corners of finance, or maybe maybe you're looking at graduate study or something like that. But if you do, and you start dealing with continuous compounding, you get this weird thing E, and you're like, what is E? This is the base of the natural logarithm. And so if you do continuous compounding, you would use the base of the natural logarithm. The exponent would be r, whatever the rate is, times t, t in this case would be the number of years expressed as a decimal. So if it was 1.5 years, you do 1.5. If it was 2.5 years, you do 2.5 for t. And basically, you would use that e, which is the base of the natural logarithm. This would be your exponent, the rate times the time. And then you would just take whatever that term produces and multiply times the present value to get future value. But that's only going to apply if you're doing continuous compounding, which most of the time you're probably not going to see. So unless you're doing certain types of calculations in finance, probably that's more of a side note. But I thought I'd throw that in there. Okay, so a few more things here in terms of fundamental principles. That key time value money equation does assume that the interest is not being withdrawn. So it is assuming that the interest is compounding. So what that means is you get interest, and then you get interest on the interest, and then you get interest on the interest on the interest. And so it basically keeps building, and that's what compounding is meaning. As I already noted, the compounding period and the rate per period have to be consistent with the same unit of time. So you have to make sure that you're being consistent when using the formula, or you get all kinds of goofy numbers and results that don't really make any sense. Now, if you want to solve that time value of money equation for present value, we just rearrange. And so if we solve it and rearrange it, we wind up with this. Now, this is also when it's called discounting. And I'll talk about that in a minute. So FV is still future value. PV is still present value. R is the nominal annual rate. M is the number of periods per year. M times N is going to be the total number of periods. And so basically all I did is I just rearranged that formula, did a little bit of algebra, and just shifted the formula around to find present value. And so if you do that, basically what this turns into is I'm going to take future value and I'm going to divide it by 1 plus some number, in parentheses, raised to a power, which basically means this. I'm going to take the future value and I'm going to divide it by some number that's bigger than 1. And what that means is the present value, the value today of some amount of money in the future, is less than whatever those dollars are in the future. So for instance, if it's $100 in the future, the value today, it's going to be less than $100, because I'm going to take $100 from the future and I'm going to divide it by something that's bigger than 1, which means I'm going to get a smaller value over here for present value. So that's why it's called discounting, because I take that future value and I shrink it back to present, and what I think is an appropriate amount in the present that I think is equivalent. That's the basic idea. So I'm kind of shrinking it back to the present. And the reason for that is we know $1 today is worth more than $1 a year from now. So if I think about it a little bit differently, that means the $1 a year from now is worth less than $1 today. So to find the value of $1 in the future, I need to shrink it to get back to what it is worth now. Okay. And as a little side note, if you rearrange that continuous compounding present value calculation to find present value, you'd wind up with this, where it's future value times e to the negative r times t. And that would give you the present value for a continuous compounding calculation. But you probably won't see that too often unless you go on to certain corners of finance, or you take a lot more finance classes, or you're studying in going to grad school, or whatever the case may be. Probably won't encounter that quite as much. But it is worth noting. Okay, hopefully this video has been helpful. Thank you so much for watching, and have a great day.